Okay, all of these molecules that we've been drawing actually form certain shapes that we need to start being able to recognize. And this is all based on the VSEPR theory. VSEPR stands for valence shell electron pair repulsion theory. What does that mean? That means that the charge of electrons, the clouds of electrons, repel each other. So terminal atoms move as far away from one another as possible. That's what I like to call naked boys in the locker room. Okay? It results in certain geometric shapes. Count the number of charge clouds, the bonds and lone pairs around the central atom. Each item in this list is a single charge cloud. A single bond is a charge cloud. Double bond, triple bond is a charge cloud. A lone pair is a charge cloud. One single unpaired electron can represent a single charge cloud. Each item on this list is considered one bond. A single bond, what does that mean? It's two electrons. A double bond is considered one bond. A triple bond is considered one bond. It's just a type of bond. Each item on this list is considered a lone pair, whether it's one lone pair of electrons or one single unpaired electron. So how do you predict the shape? There's 13 shapes. You have to have these memorized. You have to know the bond angles. Let's start with carbon dioxide. Okay, first of all, I noticed two locations right here on the center atom where there's electrons. I like to call them domains. Okay, there's a domain here, there's a domain here. They call them charge clouds. Okay, how many bonds did you see? Two, even though they both were double bonds. Do you see any lone pairs of electrons on the center atom? No. What's the name of this shape? Linear. What's its bond angle? 180 degrees. BF3, if you'll notice, once again, this is a violation of the octet rule, less than 8. Okay, I see three areas where there's electrons, charge clouds. Three types of bonds, zero lone pairs. We call this trigonal planar. Trigonal planar. And what is this bond angle right here? 120 degrees. This is nitrite. Okay, I still have a double bond here and a single bond here. That means it resonates, right? Bond order would be 1.5. So this counts as a domain. This counts as a domain. This extra pair of electrons also counts as a domain. So that's three domains. I've got two bonds and one lone pair. What do we call that? Bent. This bent angle right here has a bond angle of, an ideal bond angle of 120, okay? But since this extra pair of electrons is pushing and repelling harder on these two atoms, this angle is more probably going to be like 117. Methane. I see 1, 2, 3, 4 charge clouds, or domains, 4 bonds, 0 lone pairs. We call that shape tetrahedral. What's this bond angle here? It's 109.5, but I just kind of call it 110. I round up. This had 4 domains right here. Here's 1 bond, 2 bond, 3 bonds, and then here's another domain right here where there's electrons, the lone pair. So it's got 4 domains, 3 bonds, 1 lone pair. We call this trigonal pyramidal because it's a triangular pyramid that goes upwards. Here's the extra pair of electrons. This angle is a little bit less now than 109.5. We call it 107. Here's water. Water has 1, 2, 3, 4 areas where there's electrons. So 4 domains, 2 bonds, 2 lone pairs. We call that bent. This bent angle, once again, these 2 extra pairs of electrons are repelling on these atoms, forcing this bond angle to be less than 109.5, less than 107, 104. Now we're getting into the shapes that have violations of the octet rule. This is more than 8 valence electrons. So I see 1, 2, 3, 4, 5 areas where there are electron clouds. 5 bonds, 0 lone pairs. We call that trigonal bipyramidal. This is what it looks like from the side. This is what it looks like on top. The bond angle for this one is going to be 90 degrees. The bond angle for this angle right here is going to be 120. SF4 has 1, 2, 3, 4. It also has 5 domains, but now it's got that extra pair of electrons right here. So it's got 5 charged clouds, or 5 domains, 4 bonds, 1 lone pair, and we call this shape seesaw. This is what it looks like from the side. This is what it looks like on top. This bond angle right here, we still have this extra pair of electrons pushing down on these guys, so it's probably a little bit less than 120. I'd probably go with 117. This bond angle right here is still 90, however. ICL3, once again, 1, 2, 3, 4, 5 domains, 3 bonds, 2 lone pairs. We call that T-shaped. Why? It looks like a T, just like that. Then we have 1, 2, 3, 4, 5 for xenon difluoride. It's got 5 charged clouds, 5 domains, 2 bonds, 3 lone pairs. This is just called linear, just like the first one we did. That's going to be a bond angle of 180 degrees. The last one is when we have 6 charged clouds. 1, 2, 3, 4, 5, 6. Sulfur hexafluoride. Has 6 charged clouds, 6 domains, 6 bonds, 0 lone pairs, and we call that shape octahedral. All the bond angles are 90 degrees. Looks like a jack. If I take one of these guys off, then I still have 6. I have an extra pair right here, so it's 6 clouds, 5 bonds, 1 lone pair. We call that square pyramidal. Why? Because we have a square in the x-plane, and it's going up to a pyramid right here, square pyramidal, 90-degree angles. XeF4, or xenon tetrafluoride, is going to look like this. I got 2 extra pairs now, so it's going to be 4 bonds, 2 extra pairs. We're going to call that square planar, just because it looks like a plane square. Compounds with multiple central atoms. Look at each central atom on its own. Everything it is bonded to is considered to be a terminal atom. Count the charged clouds and bonds around it. Predict the shape around it. Isolate it. This is really simple. If I'm looking at this guy right here, this carbon is doing what? 1, 2, 3 domains. That's called trigonal planar. This carbon is doing what shape? 1, 2. That's called linear. This carbon right here is also doing 1, 2, 3, so this is called trigonal planar. So I have basically a trigonal planar attached to another trigonal planar with a linear in between. Trigonal planar, linear, trigonal planar.